Bam! Mr. Tarrou. In this video, we're going to do 3 examples involving finding unit vectors and determining whether a couple of vectors are indeed collinear. I'm going to include timestamps in the description so you can jump ahead to any of these 3 examples we're going to do. You'll also find a link to a playlist that includes all of my videos so far that involves vectors. So what is a unit vector? Well, it says here, probably in your textbook, something like this. If vector v is equal to v sub 1, v sub 2, this is of course a column format for a vector. I say of course, actually a lot of textbooks don't use this notation, that's why I'm describing it. You might see this notation as with some chevron brackets, v sub 1, v sub 2, indicating movement along the x-axis and y-axis. Well, if vector v is, some type of vector, then the unit vector in the direction of a non-zero vector v, a non-zero vector, a trivial vector. Remember, vectors are a directed line segment, and a non-zero vector is just a vector where the initial point and terminal point are the same. Therefore, it can't be a directed line segment. It can't have direction. Therefore, we have to be looking at a non-zero vector v. Well, to create that unit vector, which goes in the same direction as v, but has a magnitude of 1, well, the formula there is take vector v and divide it by the magnitude of vector v, or in other words, do 1 over the square root of v sub 1 squared plus v sub 2 squared times, this is creating a scalar multiple that you apply to that vector in its component form. And what you're really doing, if you remember us representing vectors geometrically, is you're taking, say, a vector that, I don't know, maybe goes down to the right and has a length of 5. Well, if you have a vector with some horizontal and vertical component that has a magnitude of 5 and you divide that magnitude by 5, you're just simply going to get another vector that goes in the same direction but has a length of 1. And that's what a unit vector is. Now, collinear vectors, well, that's 2 vectors where we have vector u, which is u sub 1, u sub 2, and vector v in its component form, v sub 1, v sub 2, are collinear if vector v is equal to some scalar multiple of vector v, or vector v is equal to some scalar multiple applied to vector u, where k is some scalar multiple. Well, that's exactly what we're doing in our formula for calculating or creating a unit vector. We're just taking some vector v, multiplying it by some scalar multiple. This is giving us a way of creating another vector whose magnitude is 1, and you get another vector which is going in the same direction, and thus, collinear. But there's a difference between 2 vectors going in the same direction and two vectors which are collinear. If k, your scalar multiple, is greater than 0, and vector u and vector v, therefore, they have the same direction. So we're looking at a couple of vectors, well, like I did here in green and white, going down to the right. If k is a positive scalar multiple, you're going to get another vector going in the same direction. And if k is less than 0, well then vector u and vector v have opposite directions. So if you wouldn't want to actually, this isn't the formula, but if I come through here and I say, well, let's make this scalar multiple negative instead of positive, well, you're going to get a vector that's not going in the same direction, but going in the opposite direction that has a magnitude of 1. So remembering that vectors are directed line segments, you would have 1, 2, and 3 points that are all falling within the same line. So collinear, it's like vectors that go in the same direction are kind of like a special case of collinear vectors. Collinear vectors do not have to go in the same direction. They have to have, they could be placed such that their initial points and terminal points are all lying within the same line. Now, we don't say that as a definition because a vector is defined by its direction and magnitude, not its initial point. So those initial points don't really have to be the same point. Thus, we're not really checking whether or not 3 points, being whether they're the initial or terminal points of those vectors, all fall within the same line, but just that one vector is a scalar multiple of another. So let's get on to those three examples right now. So here we go. Example 1. Given that vector p is equal to -4, 1, find all vectors with a magnitude of 3 that is in the same direction. And then for part B, find all the vectors which are collinear, and again have that magnitude that's equal to 3. So we basically want to first find the unit vector for vector p. Why? Because if we sort of standardize this vector, if you will, and find another vector with a length of 1 going in the same direction, then we can take that unit vector and simply multiply it by 3 and have a vector going in the same direction as vector p, but has a length of 3, really simply. So our unit vector, step 1, it's 1 over the magnitude of the given vector. So it's going to be 1 over the square root of -4 squared plus 1 squared. That's going to set up our scalar multiple that reduces the length of this vector to whatever its magnitude is down to a magnitude of 1. Well, we have, of course, the square root of -4 is 16, the square root of 1, So we have 1 over the square root of -4 squared, which is 16, plus 1 squared, which is 1. Well, 16 and 1 is 17. And here is our scalar multiple. This vector has a magnitude, vector p has a magnitude of 17, so we're simply going to apply the scalar multiple of 1 over the square root of 17 to that vector p and get a unit vector. Now, if we take that vector and multiply it by 3, we're going to have a new vector whose magnitude is equal to 3 and goes in the same direction as vector p. Also running out of room here a bit. And I'm going to call this vector q just so we can change some of the names and hopefully make this clear. So we have 3 times -4 is -12 over the square root of 17. And we have 3 times +1 over the square root of 17. And this vector, either you call it 3 times the unit vector, which we derive from vector p, or vector q is going to be a vector which is going in the same direction as vector p. So that vector is, you may include the name in your work or not, but probably more than likely you could just write the final answer without even naming it. Depends on what your teacher wants. So this vector is going in the same direction again and has a magnitude of 3. Now, what if I want all the collinear vectors? Well, we already have one of them, the vector that's going in the same direction. But you can also, with collinear vectors, they don't have to go in the same direction, they may also go in the opposite direction. So if this is vector q, then the other answer is negative of vector q, which means we're just simply multiplying this by a scalar multiple of -1 and get +12 over the square root of 17 and -3 over the square root of 17. So as long as you're just dealing with numerical values, that's all there is to finding unit vectors and finding all vectors that go in the same direction as a given vector, or other vectors, all the vectors, are going to be 2 of them, which are collinear. Well, 2 of the vectors as long as the magnitude is at a fixed value. For our second example, we're going to show that the points of A, which is -2, -2, B, which is 2, 0, and C, which is has the coordinates of 8, 3, are collinear. Now this problem doesn't start with vector notation or with vectors. It's not a vector application problem necessarily, like a word problem. It's just asking you a question. So really, even though I'm going to show you how to solve this problem with vectors, if you have the flexibility in your work, you don't have to. But then again, it's nice to develop our new learned skills on problems that we can easily check with older skills that we already know. Like, hey, A is at -2, -2. So if each of these tick marks is 1 unit, down our left 2 and down 2, and we have coordinate A, or point A. Point B has the coordinates of 2, 0. And C has the coordinates of 8, 3. So over 1, 2, 3, 4, 5, 6, 7, 8, and up 3. You know, doing a quick sketch here, we could check out the slope from A to B, the slope of that line segment, which is going to be 0 minus -2 over 2 minus -2, which of course is going to give us what? 1/2. And find the slope. It looks like measure from an angle, but I'm writing them for slope, of AC, that line segment, and that is going to be 3 minus -2 and 8 minus -2, and we get 5 over 10, which of course reduces down to 1/2. Now, since we've checked the slope from A to B and A to C are equal, these 3 points we already know are collinear. Let's see. Oh, by the way, you wouldn't want to check this by doing the slope of AB and the slope of BC, because that segment BC could be off some, well, actually, scratch what I was about to say, because you couldn't have 2 different points with the same coordinate or label of B, but I like this way of checking the slopes better. So now that we know that these 3 points are collinear, how can we do this with our new knowledge about vectors? And that formula I just gave you on the previous page, where if one vector is equal to a scalar multiple of another vector, then they're collinear. If that scalar multiple is positive, same direction. If that scalar multiple is negative, they're going in the opposite direction. Well, we just simply need a couple of vectors. So vector AB, depending on the notation and the way your teacher is covering it for your class, they may be just simply looking at saying, well, they might be using this notation as well. I kind of want to get away from this notation because my current textbook is not using this, but I know a lot of textbooks do. You use these chevron brackets and you look at the horizontal movement first, so it's going to be terminal minus initial point, so it's going to be 2 minus -2. And the same with the movements along the y-axis. This is the movements along the x-axis. 0 minus -2. And we get vector AB, which is equal to 4, 2. If you're writing this as column vectors, that is going to be your movement along the x-axis, your movement along the y-axis, and the mathematics are just exactly the same. So it's going to be 4 and 2. Your textbook might also be creating and working out the position vectors for each of these coordinates, where you have OA. If you watch all my videos, this is becoming repetitive, but just in case, as I learn that different textbooks use different notation. Position vector for point A, position vector for point B, position vector for point C, and then with all of that, if we want vector AC, and I want to use that same initial point again, then that is going to be the result of doing vector OC minus vector OA, the position vector for C, minus the position vector for A. Again, Take 2. No, OC is 8, 3. And that's going to be 8 minus negative 2, which is 10, and 3 minus negative 2, which is equal to 5. Now, you saw in that previous example, when we apply a scalar multiple, that scalar multiple has to apply to each of the components of the vector. So as we look at the components along the x-axis, that ratio for those two values needs to be the same as the ratio between the components for the movement along the y-axis. So we have, let's do this in green for the movements along the x-axis. We have 10 divided by 4 is equal to 2 and 1/2. And for the components along the y-axis, we have 5 divided by 2, which is again 2 and 1/2. And since we have the same ratio for the components along the x-axis and the y-axis, we have a scalar multiple. We have that AB, vector AB, is, well, we take that smaller vector and multiply it by, well, let's just call it 5/2. Five-halves vector AB is equal to vector AC. Therefore, vector AB is collinear to vector AC. Therefore, A, B, and C are collinear. When you're doing these problems that say show that, you're going to have to validate your answer both with algebraic work and then summarizing your conclusion at the end of your problem, and that is the end of this second example. It's the last example. Find the values of A such that the points A, which has the coordinates of A, comma, A negative 2, minus 2, and B, which is 2A1, and C, which is 0, 3A, are collinear. Okay, so here we're stepping up in difficulty. Obviously, we have everything's written in variables. And does that change the way we do the problem? Maybe we can't graph these points on a coordinate plane and know exactly where they're at, but you saw the foundations in the previous example. Just set up a couple of vectors using the same initial point, and it doesn't matter if that point is sort of like on that previous example, we could see that A was the farthest less point, and we just found vector AB and vector AC, and there was some kind of magic in knowing which coordinate was farthest to the left or the right. Remember, you could have picked the point in the middle. And collinear allows that scalar multiple to be either positive or negative, just as long as it's a scalar multiple. So, you know, the one vector is a scalar multiple of the other. So there's no magic in saying, well, I know that this is going to be my initial point, or this is going to be my initial point, or C is going to be, just one of them is fine. So we're going to set up vector AB. So there was no magic, I just want to go in alphabetical order. But vector AB is going to be this x-axis component minus this x-axis component, terminal minus initial point, and again for the y components, or the I and j components. So that's going to be vector AB, and that simplifies down to be, well, just simply what? 2 minus 1 is 1, so A. And here we have negative times negative is positive, so we have 1 plus 2 is 3 minus A. And vector AC, subtract those horizontal components. I'm going to try and say x, y, and ultimately we're doing 3 space as well. So I'm going to pull away from the idea of saying horizontal and vertical component because it gets a little funny with 3D space, but the x component, 0 minus a, in case you were wondering why I kept saying x and y instead of horizontal and vertical, 3a, terminal point minus initial, and vector AC is equal to 0 minus a, which is negative a, and 3a minus a is 2a, and negative times negative is positive, so we have 2a plus 2. Now, those are scalar multiples of each other. You know, how am I supposed to find a specific scalar multiple, like the previous example, which was 5/2? Oh, well, I'm not going to find right off the bat a specific scalar multiple. I'm kind of glancing to make sure I didn't write something silly in these answers and carry through a mistake to the rest of my example. No. What did you do? What did we do in the previous example? Even though it was kind of obvious because they were whole numbers, we, in the same direction, if you will, from, in this case, we'll do AC over AB, divide out the components for the x-axis and the components for the y-axis and make sure that those ratios are equal. So we're going to have negative a over a. So these are the division of the x components. And that ratio has to be the same as what you get, as long as you go in the same direction, as dividing out or finding the ratio of your y-axis components. Like in that previous example, one more time, if we had gotten a ratio of 5/2 and 7/2, then there wasn't a constant scalar multiple that connected or related all of those components, corresponding components of those two vectors. So these ratios have to be the same. So all we have to do now is solve for a that would, you know, create equal ratios. And your problems, I made this up for the video. It was inspired by a problem in my textbook, but it's not the exact same thing. You might have to do cross multiplication and solve this out. And I didn't do this intentionally, but as it came out, when I set this up, well, we have negative a divided by a, which is negative 1. Now you distribute that 3 minus a, you multiply that to both the left and the right-hand side of this equation. You may be calling that cross multiplication, with this being over 1. But we have negative 1 times negative a, which is positive a, and negative 1 times 3, which is minus 3, equals 1 times your 2a plus 2. Let's go ahead and subtract both sides by a, and subtract both sides by 2. And we have a is equal to negative 5. And that's what the question asks for. Find the value of a such that these points are actually collinear. And if you want to check your answer, I mean, I got an answer, but just because I did it doesn't mean it's right. I had to reshoot one scene of this video because I miscopied something. Let's go ahead and plug that back in. If we say that a is negative 5, well then vector AB is what? Negative 5, 3 minus negative 5, or 3 plus 5, which is 8. AC then is going to come out to be negative a, and a is negative 5, so negative negative gives us a positive 5. Oh man, am I in trouble? Because that x component, that component along the x-axis is negative, and this one's positive. Maybe we made a mistake. But we have 2 times negative 5 is negative 10, plus 2 is negative 8. And as you compare vector AB to vector AC, we see that our scalar multiple is just simply negative 1. Thus, AC is a scalar multiple of AB. And we could write a summary statement, but this question simply said find A. We found A, we checked it, we got the right answer. I'm Mr. True. Bam! Go do your homework.